Hello, ladies and gentlemen, and thank you for joining me once again. We're looking at the Euclid contest from the year 2002, and we're up to question number 7, which has both a light bulb and a written portion. Alright, 7a. In the diagram, we got a triangle here. AC is 2x, and BC is 2x plus 1. And this angle, ACB, is 30 degrees. So immediately, I start thinking 30, 60, 90 triangle. Now, I haven't been told this is a right angle triangle, but 30 degrees, that's fairly suspicious. Okay. If the area of triangle ABC is 18, what is the value of x? Alright. So, area of a triangle. So, I'm thinking that we'll have to use this information, otherwise they wouldn't have given it to us. But we should start thinking, okay, how do we get the area of a triangle? Now, we're presented with two sides and a single angle here. And what ways do we know in order to get the area of a triangle? Well, the simplest way to get the area of a triangle excuse me, is 1/2 base times height. So let's see what we can do with that. It might not be the right formula. There are other ones. This Heron's formula certainly comes to mind, but let's draw our picture here. So we have, I think, A, C, and B here. Doesn't particularly matter, but I'm pretty sure it was that order. So we got to 2x, and we have 2x plus 1. Now, if we had a height here, well, we've got a base, 2x plus 1, so 1/2 base times height. One-half base times height. So is there a way to get that height in terms of x? Because then we'll have a single equation in x, and we can hopefully solve for it. Well, I notice here now, if we call this brand new point D, I notice ADC is a right angle triangle. And in fact, it's going to be a 30, 60, 90 triangle. So my initial jump on that 30 degrees sort of proved true. So it's a very, very common, on math contests, triangle. It's got interior angles of 30, 60, and 90, and the side lengths, and this is a set of ratios you should probably remember, are 2, 1, and √3. This is also a great way to remember, so the sine of 30 degrees is opposite over adjacent, or opposite over hypotenuse. Cos 30 degrees is adjacent over hypotenuse. It's a great special triangle to have memorized, even if you just want sines and cosines out of it. But it's useful for math contests, and I do highly recommend people memorize the 30, 60, 90 triangle. Okay. And the 2 is always on the hypotenuse, because it's the bigger one, and 1 is always less than √3, so it goes across from the smaller angle. Shorter side gets shorter angle. That's how I remember it. Okay. So that means that if we have 2 over here for the hypotenuse, here we've got 2x. So 2x is to 2 as h is to 1. So, actually we'll keep it in black. So we get the same ratio here. Okay, the things opposite 30 have the same ratio as the hypotenuses. But of course this is just x, and this is just h. So h is equal to x, and now we can plug that into our area formula. 1/2 2x plus 1, x. Bring the 2 over to the other side, multiply by 2, bring it to cancel out this half. We have 36, and then 2x squared plus x. And I think we have the makings here of a quadratic equation. Okay. And you can do whatever you want. You can try and factor this, or you can use the quadratic formula. I use the quadratic formula a lot, so let's try and factor it. If we want to have nice factors, if the factoring fails, then we'll use the quadratic formula because it always works. But it's good practice. So if it's going to factor into something nice, we're going to have the 2x and an x split up. Okay, and now we need to start thinking of things that multiply to negative 36. And then, ooh, okay. So what things multiply to negative 36? I'm thinking 36 negative 1, negative 12 and 3, these sorts of things. And I need 2 times 1 adds up to the other. I think a 9 and a 4, because they double the 4 and it differs by 9 by 1. So now I need to make sure I get the minus sign in the right place. So the 9 is bigger than the 2 times 4 is 8. So he should have the plus and he should have the minus. So either x is 4 or x is negative 9 over 2. Obviously x is positive, because otherwise we wouldn't have positive lengths to make a triangle. So x is going to be 4. Okay. That wasn't the most pleasant factoring, but wasn't that bad. Quadratic formula, as I always say, would have gotten it out immediately in basically the set amount of time. So it's always something you should know. So that was A part. X was 4. That was all we were asked for, right? That was the value of x. Okay. And now B part, which is long and has a picture associated to it. So let's get cracking. A ladder, AB, A up to B, is positioned so that its bottom sits on the horizontal ground and its top rests against the vertical wall. Okay. In this initial position, the ladder makes an angle of 70 degrees. The bottom of the ladder is then pushed 0.5 meters to a new point A prime, and then because the ladder is rigid, it's a fixed length here, it'll slide down to a new point B prime. Okay. In this new position, the ladder makes an angle of 55 degrees, as shown down here. Calculate to the nearest centimeter. Okay, so right there I pause for a moment. Centimeter, I need to keep track of units. So I'm given some stuff in meters. I might want to convert that from 0.5 meters to 50 centimeters, because there's 100 centimeters in a meter. Okay. So calculate to the nearest centimeter the distance that the ladder slides down the wall. That is this length from B to B prime. We know A to A prime. All right. So we got 2 right angle triangles here, and we know some angles, 55 and 70. We don't know the length of the ladder. So I would say, first things first, let's convert the 0.5 meters into 50 centimeters and redraw our picture. That way we're keeping it in the units they want. They want nearest centimeter, so let's only work in centimeters. So we have B and A, and then it gets pushed out to A prime, and this distance here is 50 centimeters. Okay. So the first thing I note is the ladder is rigid. So the length AB is the same as the length A prime B prime. So I know that whatever the hypotenuse for these right angle triangles is, I know it's the same length. Okay, they share the same hypotenuse. They don't share the same legs or the same angles, but they definitely share the same hypotenuse length. Okay. So I'm going to let L be the length of the ladder. And Okay, they already gave us C down here. I was about to say let's add in a point called C, but they already got one here. Okay. So, we have L here, we got L here, so we have two lengths L. Now we don't care what L actually is, but we'll probably have to figure it out on the way to the calculation of what we do want, which is B and B prime. Okay. Now, I'm starting to think trigonometry, and I'll tell you why. What we had here, 7a, we dropped a perpendicular down, and we basically used our special triangles. But essentially what we would have done if we didn't have similar triangles memorized is we would have done 2x times sine 30 degrees. So I'm thinking we should have some sines and some cosines in here. That's what I'm thinking. Yeah, so going back to our picture, we have a right angle triangle. Opposite, adjacent, here's our angle, H. Sine of our angle is opposite over hypotenuse. It's called SOHCAHTOA. It's something that, at least when I was going through school, you learned in grade 10 trigonometry. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. All right, these are probably things that we're going to need in this question. So, B prime C, this length here, the shorter length, the shorter height, is, well, hold on, let's write it out with SOHCAHTOA. So sine 55 degrees is going to be B prime C over B prime A prime, which is B prime C over L. So L, sine 55 degrees, is B prime C. Similarly, L times sine of 70 degrees is BC. So the length we want is BC minus B prime C, which is, we can take out a factor of L. We'll have sine 70 minus sine 55 degrees. So both of these values, while not nice exact things like root 3 over 2 or root 2 over 2 or anything like that, they are numbers that we can punch in on our calculator. And because they aren't going to have nice exact expressions, that's likely why they asked us to round to the nearest centimeter. Okay? But we can plug those values into the calculator. I can punch in sine 70 degrees and my calculator will give me everything. So the only unknown here is that L in the equation. So if we can work out what L is, maybe we'll be all set. So is there a way to get L? So we can get L, plug them in, and we're all done. Well, so we got that difference with sines. We can actually get these lengths down here. AC is going to be L cos 70, because it's adjacent to the angle over the hypotenuse. So once again, if I have a right angle triangle, cos of my angle is the adjacent over hypotenuse. And so that means that AC is going to be L cos 70 degrees. And A prime C is going to be L cos 55 degrees. Okay. So this one's the longer one. So A prime C minus AC is, take out the L again, we'll get L cos 55 degrees minus cos 70 degrees. So why did we bother to do that? Well, we know what A prime C minus AC is. We know that that's 50 centimeters. So 50 centimeters is L cos 55 minus cos 70. Rearranging, we can solve for L. L is going to be 50 centimeters divided by this difference. So BC minus B prime C, the distance we're looking for, the one that we want, is going to be L. Well, that's 50 centimeters over cos 55 minus cos 70 times sine 70 minus sine 55. And now we only have numbers, so it'll all work out. And these cosines and sines, they're exact values. They don't have units, so we are just going to end up with something in centimeters. I will note, however, that I didn't just work out L and round it and then plug it in. I'm keeping everything where everything as exact as possible until the last moment when I have to round. So if I plug that in on a calculator, I will get approximately, let's see here, sine 70 minus sine 55 divided by cos 55 minus cos 70 times 50. So I get about 26.028, and there's a 3, so we'll just round down to the 8 centimeters. So to the nearest centimeter, the latter slides down 26 centimeters. Okay? And that wraps that question up rather nicely. So that's the B part, and we explained everything we were doing. We even did a little example to show our SOHCAHTOAs and where they were coming from. Yeah. So we used sines to get this difference, and we used cosines to get this difference. And because this difference was known, we could get that L value, although we didn't actually solve for L, but we used it in our final calculation. Okay. Nice little question overall, and hopefully question 8, which we're going to do in the next video, is equally nice. So thank you guys for watching, and hopefully you'll join me in the very next video for question 8.